Okay, so we've defined what a limit is, and what I would like to do now is just kind of reassure you that for most of our functions, for example, how would I compute the limit as x approaches 3 of x squared? Well, x squared is a polynomial that's a very um, nicely behaved function. It's a nice parabola, right? And so Um, if we approach x equals 3 from either side of 3, we probably already know what this is not to scale, by the way. We already know what this is going to be, right? That's just going to be 9 because if we insert 3 into x, for x, we'll get 3 squared is 9. So for nicely behaved functions, um, if you're trying to compute the limit and you can just substitute in the value and get something defined, um, then the limit is probably going to be that number. We're going to see some cases, some special cases where that's may not be the case, but um, I think it's kind of satisfying to know that in a lot of cases with nice functions here, our limit is going to be able to be computed just by substitution. Okay, so another example we had earlier, x approaches 2 of x squared minus x plus 2. We showed that that was 4 geometrically last time. So in this case, if we just put in 2, we get 4 minus 2 plus 2. And so that's equal to 4. Okay, we're going to develop techniques for computing the limit in the next section, but I just wanted to give you kind of a hint before we get started on some weird cases. Well, maybe not weird cases, but cases where it may not be so easy to see. And so in that vein, let's take a look at an example here. Let's see if I can cover up some stuff so you can't see everything at once. I'm going to show you a numerical table that we're going to explore here. So suppose that I'm taking a look at this function, the square root of t squared plus 9 minus 3 over t squared. And I'm asking myself, well, what happens as t goes to 0? You can see here, this is kind of a shortcut. We're taking t at both the positive side and the negative side, and we're computing some numbers. And so our usual game that we play is as t goes to 0 now, as t goes to 0 from either side, maybe plus or minus was going to mean from the right or the left. I'm going to define that in a second too. What do my y values do? Well, it looks like my y values are going to 0.166, which is actually 1/6. Okay, we might say, well, I'm all done. Well, somebody else might come along and say, well, wait a minute, maybe I need to compute t approaching 0 for more values of 0. And so, or t for more values of t. So what happens now as t gets even closer to 0? What do we see here? What the heck is this? And so now at this point we might say, well, my y's are going to 0. My y's not going to 1/6, y's going to 0. And so this is actually, if you try to put t too close to 0, what's happening here? You're ending up dividing by a number that's very, 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 very small, right? Like what happens if you take 1 divided by, let's say this is just maybe 1 over a million. What's that number going to be? That's right, it's going to be a million. Okay, this number didn't blow up on us, but what happens is that as you get smaller and smaller, as your denominator goes to 0, what happens is you end up building up some what's called a round-off error in your calculator, and your calculator may not be able to handle the numerical computation. And so this is actually computational error here, which you would not know generally, right? And so the purpose of this exercise is to tell you that sometimes numerical values will lead you astray. In this case, it will turn out, we're going to be able to solve this algebraically in the next section in 2.3, but it does turn out that the limit does turn out to be 1/6. I keep saying turn out. Okay, good. So calculators may lie. That was the upshot of that example. Let's talk about when some other limits might not exist. So we said before that in order for the limit to exist, I should be able to go from either the right or the left and come up with the same number. Well, what happens, or what does it look like if the limit coming from the left is different from the limit coming from the right? What would that look like? So here's an example. You might have a limit up here. Maybe call it L1 for big limit 1. So this limit, this function has a limit then as x approaches 1 from the right. How about from the left? I'm going to make it so that the two things are different. And so here's an example of what you probably would see. And then again, at the point x equals a, it doesn't really matter where we put the solid dot. So open circle means that it's not defined at that point, right? Okay, and so this kind of a jump is typical. What we would say is, in this case, the limit as x approaches a from the left, that's our notation now, a from the left of f of x, in this case, is equal to L2, and the limit as x approaches a from the right of f of x is equal to L1. And in our example here, L1 is not equal to L2, and so we would say that overall, let me see if I can spell correctly, overall, the limit does not exist. So we'll abbreviate does not exist as DNE. And the reason the limit does not exist is because if you come in from either side, you get different answers. So for the limit as x approaches a of f of x to be equal to L, we must have that the limit as x approaches a from the right or the left of f of x is also equal to, they're both equal to L. They both must be equal to the same point. Very good. So let's do one more weird example maybe. And then in the next video, we're going to take a look at some more template examples. So suppose I've got a curve. This curve is known as the topologist sine curve, and it's defined by sine of pi over x. Okay, so at x, if x is equal to 1, what function do I, or what value do I have? Sine of pi is equal to 0. So the curve is going to go through this point. It's actually going to come, it's going to look something like that. And now, what are the zeros of the sine of pi over x? The zeros are going to be where sine pi over x is equal to 0. And so think of this as like the sine of a equals 0. Then a is equal to 0 plus or minus pi, plus or minus 2 pi, plus or minus 3 pi, etc. Okay, so in this case we have pi over x is equal to 0 plus or minus pi, plus or minus 2 pi, etc. Right? So this means that I'm going to go ahead and divide by pi and put a 1 there. So that's going to be 0 plus or 0. I'll say 1 over x is equal to 0 plus or minus 1 plus or minus 2. Okay, so that means that x itself, 0 is not going to, I can't take 1 over 0, so that one goes away. But this one will stay here, plus or minus 1, plus or minus 1 over 2, plus or minus 1 over 3, plus or minus 1 over 4. Plus or minus 1 over 5. What's happening to the zeros of my function? Well, they're going from 1, 1/2, 1/3. Can you see that? 1/4. And so what's going to happen then is my curve is coming in. It's oscillating between plus or minus 1, and it's oscillating faster and faster and faster and faster and faster and faster and faster, and it never stops. It's oscillating between minus 1 and 1. And the same thing, because the sine is, this is going to be an odd function, right? You're going to have the symmetry on the other side. Um, well, we won't graph the other side just to save a little bit of time. But so the question is does the limit exist? Does the limit as x approaches 0, let's just say from the right, of f of x exist in this case? And so let me give you the wrong explanation and see why it's wrong. Here's the wrong explanation. The limit is any number between -1 and 1 because we said that we could make the y values approach that number by taking x sufficiently close to 0. So for example, I could say that the limit is 1 because if as x gets very close, right, my y values are still coming into 1. They go away from 1, but they're coming into 1 as well. And actually, I gave away the reason why this is not true. Did you see the false argument here? When we say that the values of y approach a certain number, that means they can't leave that number. They have to stay close to that number. So for example, why is this point not a limit? Is because I can't force the y's to stay here as x goes to 0, right? As x goes to 0, they bounce out of that area. And so if the limit exists, if the limit does exist, it is a single number. Okay, so if the limit does exist, it can't be like the entire interval from -1 to 1. It must be a single number. And so this is kind of a good example of a weird thing that can happen with the function that may look like the limit does exist, but it does not. So in this case, the limit does not exist as x approaches 0. As x approaches 0 from the right, the limit does not exist. Okay, so I've gone way over. In the next example, we'll take a look at some more template functions.